All right, let's get started. Welcome to Build Day 3. Thank you for coming this early. My name is Max McMullen. I'm the development lead for Direct3D and DXGI. My team designs and implements the Direct3D runtime. We also work with hardware vendors to design new rendering features. In Windows 8, we designed, implemented, and shipped Direct3D 11.1 for the Windows 8 platform. And we're here today to talk about performance tips for Windows Store apps using DirectX and C++. It's a long agenda, so let's get started. 4 parts to the talk. Just a high-level overview. What are we talking about with Windows 8 performance measurement, specific to the DirectX and C++ Windows Store applications. 2, let's talk about what's new in measuring rendering performance in Windows 8 and Windows RT. New platforms, new hardware, there are new requirements in how you measure things on the system. 3rd, Surface, all the new Windows RT systems, new hardware platform. There are a lot of new characteristics of these power-efficient GPUs that we've enabled on the platform. We're going to have some specific optimizations, how to tune for those new power-efficient GPUs. And then finally, we'll talk about those specific optimizations. So, high level, what's new about optimizing for Windows 8 and Windows RT? As I mentioned, it's both a new software platform and we're targeting new hardware platforms with Windows 8 and Windows RT. On the hardware side, we've enabled these really long battery life, really power-efficient platforms. And what that means is they have typically single-chip integrated graphics, shared memory bus. They sip power. And to get there, there's some trade-offs in the rendering capabilities. So the other thing, we have a 60 hertz target for the OS. So constantly updating, fast and fluid, seamless UI experience on these low-end platforms. In terms of the Windows operating system itself, the good thing to know is that DirectX is now used to get every single pixel on screen. The desktop compositor is always enabled. It's always ready to compose the UI. The charms bar, your application, split screen. So DirectX is now used at every single layer of the stack. If you're writing a Windows Store application, DirectX is the foundation for every single way to write a store application. WWA, XAML, and then DirectX C++. Finally, as I mentioned, Direct3D 11.1, the big area we focused on is adding new APIs to optimize for these power-efficient GPUs. We have both tiled and immediate renderers now on the platform in significant numbers, and it's important to know how to optimize for each type of GPU. So let's just talk about all the different ways of writing a Windows Store app briefly. We're here to talk about DirectX and C++, but sometimes you don't actually have to write every single piece of code in Direct3D, and my team has worked with all these different platforms to highly optimize them on these new hardware form factors. So WWA, built on top of IE technology, highly performant, fully leverages Direct3D 11.1. Once you start talking about XAML, XAML is, again, fully optimized, uses Direct3D 11.1, and it uses Direct2D. Now we're talking about interoperable graphics, where with XAML, you can actually target XAML for your UI. You can use the swap chain background panel for doing underlying 3D rendering. You can use Surface Image Source for providing content to specific entries in the actual scene graph in XAML. Let's say you want to go a level lower. We have Direct2D and Direct2D Effects, which is new in Windows 8. Highly optimized vector graphics rendering. Direct-Write with optimized text. Direct2D Effects has optimized image processing. You can generate any type of image scene graph you want and get fully hardware-accelerated image processing. That said, we're here to talk about DirectX and specifically Direct3D 11.1 and C++ applications in Windows Store. And sometimes you actually really have to use Direct3D to get the full power of the hardware to get that 60 hertz fast and fluid seamless experience you want for your application. For the rest of the talk, I'm going to make a couple assumptions. It's just to fit in the time. This is 400 talk. I'm going to make some of these basics. I'm assuming you've actually built a store app before with C++ and DirectX. If you haven't, there's some earlier talks at Build that are great to go look at. You can watch the videos online in a couple days. Second, I'm going to assume you know Direct3D fundamentals. It's a really big API, has lots of cool features. It just, tutorials are kind of hard to go through at the same time as we dive deep into these performance aspects of the API. There's another talk at Build that will help with that, as well as some references at the end if you need to brush up on D3D. Okay, measuring rendering performance. How do you measure rendering performance? It varies from platform to platform. There are a bunch of basic techniques that I'm sure you're familiar with that translate well across platforms. But Windows 8, Windows RT, we have some tools that we used on the D3D team that are publicly available, and those will help you optimize your app to the full extent. So, Windows, we have a really broad developer ecosystem, lots of tools available to you. With Microsoft itself, we have the Visual Studio Performance Profiler and the new graphics diagnostics. Our hardware partners, all the manufacturers of the graphics processors and system-on-a chips used in Windows RT, they have their own tools. You should go look at their websites and investigate those as options. So, as I mentioned, we use a few tools and techniques on D3D that are publicly available, and actually we did a vast majority of operating system optimizations using these techniques. One, basics. Let's do tight analysis of a specific rendering technique, time measurement, iterate 100 times. There are some specific aspects to store apps to do that correctly. I'm going to cover those really quick. And then I'm going to do a lot of talking about GPU view, which is our advanced performance analysis technique. It really gives you a detailed analysis of the full graphics performance in the system. Interactions between the CPU and GPU, stalls, if you want to detect glitches. For this talk, we're mostly focused on rendering performance. Really we want to look at how much time are you spending on the GPU and how do you maximize what you're getting out of that time you spend on the GPU. Because that's where we've really added a bunch of APIs to D3.11.1 to improve your application. Okay, as I mentioned, frames per second. You might be wondering, 400-level talk, why are we talking about frames per second? It's kind of a basic thing. Well, it's a great way to dive deep into a specific shader or a specific rendering technique. It can be a bit misleading if you try to do it with too much going on in the system. Let's say you have lots of threads, you have file I/O going on. It doesn't really tell you what's going wrong in your application if you're trying to debug a technique. But it is great if you just want to play. We're all developers here. You want to try a new way of rendering. You want to put in a new shader. You want to change it and see if it goes faster. Great, quick way to do that. The key here is when you're writing a DirectX and C++ application, there are a few aspects to these applications that change how you might do this versus the past. On desktop, you typically create a full screen swap chain, and you would start presenting immediately, and you could get frames per second figures in the hundreds, 200, 300, 400 sometimes. As mentioned, the desktop is now fully composited at all times. The desktop compositor is ready to jump in to draw the charms bar. You can have two applications on screen at once. We also wanted a fast and fluid, seamless experience, so we don't want display flashes, things like that going on. For that reason, Windows Store applications are generally always windowed mode, and the compositor will force those applications to be synced to the refresh rate at 60 Hertz. What does that mean? If you're benchmarking something that is actually less than a frame time, FPS really, the old implementation won't give you any insight into how you're changing performance as you tune shaders, as you change your rendering algorithms. Really what you're after is you just want to measure time, right? You want to run the algorithm 100 times, 1,000 times, see how long it took. You want to minimize the variables that are affecting your performance measurement. And the way you do that is you get rid of as much of the system as possible and just focus on rendering. The key here is don't present. You want to mimic the rendering performance of present, but you don't want to involve the whole presentation stack in that performance measurement. When you boil the actual implementation of present down, there's a whole bunch of communication with the compositor and transmitting the data across processes. But for rendering, there's really just a flush there. You want to batch up all the rendering commands the application is issued and then send them off to the GPU. So you can swap and remove the presentation with just a flush call. The second piece to understand, again, this is meant to be a quick and easy technique for profiling specific rendering in your application. And DirectX C++ is just a low level Windows Store application, a lot of the fancy UI frameworks just aren't available. So you have the problem of how do you get output. And again, for something quick, you just want to code right away. And you also don't want a UI that's going to impact your performance measurement. My suggestion, again, this is for a quick experiment. You have the file output available to you. You can just write out to your application local directory, small, a few bytes at a time. That won't impact the measurements you're making on the graphics stack at all. If you happen to have a need for a heads-up display and some quick profiling you're doing, the key is you want the UI rendering code to not impact performance. I recommend you look at the geometry realization sample. It's available on MSDN. You can search for it. There's also a link later in resources. Inside that sample, there are a couple files, fpscounter.cpp and fpscounter.h. Those files will tell you how to cache text rendering so that you can have a really efficient just bitmap blit on screen of things like FPS or other statistics you're trying to accumulate in your application. So I actually have a brief little demo here, and we're going to use this a couple times in the talk. So in terms of demo setup, I have two machines up here. It's a very typical developer configuration. I have an x86 laptop, and then I have a Surface right here. And this, right now we're looking at the Surface, actually. I have already placed the frames per second measurement application on here. It is the basic template that if you create a new Direct3D application, this is what you'll see if you just build it and run it. I've added one thing to it, which is a profiling mode. If I tap the screen, it's going to go and start rendering the same cube, but approximately 200 times. And it's going to be time stamping the start and end. And what I do is for every 200 frames, I'll go and write out the average frames per second measurement. Actually, I output the milliseconds taken per frame to a file. So you actually have the ability to write to your local app data directory, and this is just a sample of simple output. Doesn't impact the performance of graphics rendering. Important detail here is we're approximately taking about 2.5 milliseconds per frame on this particular Windows RT machine to render the clear background in the cube. Okay. That covers the basics of FPS measurement. Let's talk about GPU View and what it can do for you. GPU View, really awesome tool. We use it extensively optimizing the operating system. We use it for optimizing Direct2D, for WWA. We use it for IE. Pretty much every single new DirectX application has probably been looked at underneath GPU View at one point in time to find all sorts of performance problems. You can look at frames per second. You can look at startup time. You can look at glitches. You can look at influences of other applications or services in the OS that might be delaying your CPU thread from issuing more rendering. Another important detail is we also use it for looking at latency. So unfortunately, I don't have time to talk about latency, but it's a really key area when you're talking about touch systems. How long does it take you to go from touching the screen to getting the pixels on the monitor to actually respond to that touch and show you an interactive user experience? As you get to increased latency of 30, 40, 50 milliseconds, you start to see objects drag and lag behind your finger. You can actually visualize that for any DirectX application using latency. You can watch on the CPU as your application picks up the input event. You can see the time it takes your CPU to process the input event, how long it takes the graphics commands to run on the GPU. You can watch the present flow from your application to the screen and just look at the time difference. That tells you what you're actually experiencing from a latency point of view. In general, GPU View, it provides a detailed analysis of CPU and GPU workloads and interdependencies. Now, what does it look like to actually use GPU View? A couple details. Installation, it's part of the Windows Performance Toolkit. You can get it on MSDN. There's a link later within an article, and inside that article are links to how to get it, how to install it, how to use it, not just for the analysis that I'm going to talk about today, but all the ways of using GPU View. It's a great article. I suggest you look at it. Other detail, GPU View is based on ETW tracing for Windows. And it can run on both Windows RT and Windows 8. Inside, after you install the Windows Performance Toolkit on your developer machine, you can find a redistributable that will let you copy over to Windows RT machine and then run it on Windows RT as well. For recording, it's really easy to use. The basic idea is you run a command file that's given to you with GPU View. You then perform whatever action it is that you want to measure, run the log file again. That will run a process where it records a bunch of .etl files and merges them into one final event log. You can then take that event log, merge .etl, and load it into the GPU View tool to visualize it. Now, this is what GPU View looks like. There's UI Chrome as well. There's a border and a menu, but really, this is what you're going to see. So, left-hand column, these are just row labels. It tells you what's going to happen to the right. To the right, this is the timeline. This is the core of visualization in GPU View. Time flows left to right. Work items generally flow bottom to top. At the bottom are your CPU threads. This is where you're issuing commands to Direct3D or some other DirectX API. So as time progresses, you'll call render, draw primitive, eventually you call present. Direct3D is a batched rendering system. We queue up commands into command buffers. Those buffers will eventually fill or are forced to go to the graphics hardware, at which point you'll see we'll get a buffer up here. This is the CPU queue representing a CPU-side queue of buffered hardware commands. And the buffered hardware commands will wait here until the hardware is ready to execute them. They sit here, they progress down in the stack until they get the next ready to run. Eventually, in the OS, there's a graphics scheduler. And the graphics scheduler will take the command, move it up to the hardware queue. Sorry. Move up to the hardware queue here. And this is where it's actually executing on the hardware. So for that actual duration of time is what it takes to render those commands on the GPU. For the rest of the talk today, when we talk about optimizations, our focus is going to be on shortening the amount of time that we spend on the actual hardware queue. There are a bunch of other optimizations, as I mentioned, latency, and we don't have time to go into those, but if you read the article in GPU View in the end of the talk, that will actually show you how to optimize for latency. Okay. Sneak preview, this is actually GPU View running. So this is the directory that Windows Performance Toolkit gets installed into. And as you see under here, there's actually a list of redistributables. And you can just grab the ARM version, drop it onto a USB key, transport it over to your RT system, and install, and that's how you get GPU View on the ARM system. So now let's switch to the Surface. We're going to do the same thing as we did last time. We're going to basically run the application. Start the logging in GPU View. And then just go back to the application for a bit and record a log of a few frames. Let me also start the profiling mode. We can actually record this in GPU view as well. Now let's go back and stop the log. So here, ETW is stopping the various sets of events that we were recording. We were recording events relevant to the GPU, to the D3D runtime. We were recording kernel events, marking transitions from user to kernel mode. All these different types of events are used to build that timeline you see on screen in GPU view. It just takes a few seconds. OK, so now you can see you have an output file, merge.etl. We recorded for several seconds, a little bit longer than usual. You can see it's a rather large file. You really want to be tight around the actual problem you're trying to measure. If this goes too long, the files get extremely large. Just something to be aware of. It doesn't impact performance that much, but it is a few %. Actually, that's so you can actually just pull it up on the surface. I've already got that same sequence recorded in GPU view here on my developer machine. I've copied it over from the surface. So we're looking at basically a Windows RT ARM platform doing the same rendering. And there are a bunch of threads and processes in the system you can see listed down here. We generally right now don't care about most of these. The ones important for the talk are the DWM, which is right here, and the frames per second measurement down here. This view right now is all the commands that are being batched when running in profiling mode. We're zoomed in. If I go out, what we see, this is a very far out view of the timeline recording what I just showed. Right here, this is approximately the application running in its 60 hertz lockstep mode, what it'd normally be if a user is using an application. Here, I've entered profiling mode. You can see the GPU work increases dramatically. The number of queued commands increases dramatically. When we zoom in, we'll see they're packed a lot tighter together. So let's first look at just the 60 hertz mode. And here's actually a really interesting part of the trace. You actually see there are 2 time intervals. This is going to match what we measured with FPS. So approximately 2.5 milliseconds of rendering time for each frame. So our quick and easy performance measurement FPS is giving us roughly the right result. So we can use it for relative comparisons if we optimize rendering algorithms. But what we also get insight into the GPU view is when we're running in this slower 60 hertz mode, these platforms are actually, they work extremely hard to optimize battery life and power. They dynamically change their clock rate at a very high frequency. And the GPU workload for this app is actually relatively low. So they can decrease the clock rate and still get a frame out in 60 hertz. So running at slower clock rates, it's actually getting 5.6 milliseconds instead of the 2.6 we saw earlier. What does this mean? Well, if you're doing really fine tuning, as I mentioned before, and you're like adding and subtracting just a few shader instructions, if you're looking at just a 60 hertz output, you may all of a sudden see that adding instructions causes the time to execute to decrease, and that's because the GPU isn't clocking down anymore. So you need to be aware of all these different variables in the system to get an accurate view of what's going on with your performance tuning. So let's zoom out and then look in at the profiling mode. So these like really power efficient platforms, they're managing a couple things. They're managing battery life, and they're also managing thermals. So you can't always be guaranteed that they won't be forced to clock down just to keep the system from overheating. If you really crank everything up, it's possible they might need to drop down for that reason as well. So currently there isn't a way to do that. I don't know if you heard the questions. I'd like to save questions to the end, but the questions were, is there any way to force it? The answer is not right now. So it's important to be aware of it and how you measure performance. So here we can see FPS measurement. We're running the profiling mode. This is the 200 frames It's all packed together very nice and tightly. The GPU is pretty much on all the time. Now we're running even faster than we were before per buffer, and that's because everything is clocked up and it's working as hard as possible. Okay, we've talked about measuring performance on the new Windows RT platform and how to start thinking about performance tuning. Let's talk about the performance characteristics of these new GPUs. What to expect with power-efficient GPUs. They're typically feature level 9.1 or 9.3. Just they have smaller compute engines, fewer features. They have limited available bandwidth compared to what you're used to on, say, x86 desktop machines. They have more rendering strategies than we've seen on desktop in a while. They have immediate render and tiled render GPUs. They've both been available on Windows before, but more than ever, we're going to see more tiled renders on the Windows RT platform, and it's important to know how to optimize for each one. Tiled render puts a little more burden on the developer to issue D3D commands in an efficient way. Finally, they have limited shader instruction throughput, again, compared to desktop. So feature levels. If you look on MSDN, you can find the full description of what it means for each feature level. In terms of performance, there are really two aspects of feature level that are important to look for. One is the maximum texture size. It's limited to 2K by 2K on 9.1, 4K by 4K on 9.3. Second, pixel shader instructions. These are maximum amounts, 64 arithmetic, 32 sample on 9.1, and then 512 on 9.3. Realistically, with these power-efficient platforms, you're going to run into real-time limits before you come close to these maximums. And what I mean by that is if you're rendering a full-screen frame and you're using a shader that's 64 instructions long, you are not going to hit 60 hertz, probably, at least on the current platforms. GPU memory bandwidth. The baseline requirement for the platform is about 1.9 gigabytes per second benchmarked. That doesn't mean the memory buses are 2 gigabytes a second. That means that's what the GPU can actually drive off the bus. These buses, so these are all usually integrated graphics. The bus is being shared with the CPU, with the display output, networking, audio. And so you can actually get about 2 gigabytes a second from the GPU. What does that translate to in terms of rendering performance? You get about 7.5 I/O operations per pixel and still be able to hit 60 hertz on the typical 1366 by 768 resolution. To give you an idea of what an I/O operation is, rendering a full screen frame, if you're just filling the screen with a solid color, you're writing a value out per pixel. That's one I/O operation. If you're sampling an input texture and writing out to the screen, that's two I/O operations, the read in and the write out. Finally, screen fill with alpha blend and texturing, you're reading in the texture, you're reading in the destination render target, blending and generating a result, and then you're writing out the final result, so 3 I/Os. So you can get approximately 2.5 screen fills with a texture and alpha blend if you're driving the full screen at that complex rendering pattern. To give you a comparison, x86 desktop integrated, we're typically talking about 15 gigabytes a second benchmarked. The buses are faster, but you can actually measure about a 15 gigabyte a second drive on them. Okay, GPU rendering strategies. Immediate renderers are what you're used to on x86 desktop again. You have a GPU, shader cores, as a memory bus, either dedicated graphics bus or it's an integrated part. And the shader cores process rendering commands, read from graphics memory, write the result directly back out to graphics memory with a few caches in between to make it optimized. No real changes here. And these same types of GPUs are available on Windows RT. Tiled renders, as I mentioned, these have been on x86 desktop before, but we're seeing far more of them on the Windows RT platform. These have a little more complexity to drive efficiently, and we're going to talk about that in a second. So how these work are the driver will actually capture roughly the entire scene of commands for a given render target. And then it'll play back those commands, dividing the render target into tiles. So in this case, these 3 tiles are already rendered. We're going to take this tile, copy it across the memory bus to the tile cache on the GPU shader core. Rendering will use a high-speed bus locally on the GPU to do all the rendering, occasionally reading from main memory as you sample from textures, for example. So now we've rendered the graphics in the tile cache. What happens next is that is written out to the tiles, and then you rinse, repeat, and load whatever tiles are left for the system, do the same pattern. So that's tile renders. We'll talk about how to optimize those in a second. Finally, as I mentioned, there's limited shader instruction throughput on some of these power-efficient GPUs. When we talk about fill rate is basically the rate at which the GPU can write out pixels. There are a number of factors that limit fill rate. One is the memory bandwidth, blend mode, shader cores, shader complexity, et cetera. Power-efficient GPUs, if you start off with a simple single instruction shader, you're going to be memory bandwidth bound. As you increase the complexity of the shader, you're going to shift the bottleneck to the actual shader processing. And we found this happens as early as 4-pixel shader instructions on some of the really power-efficient but low-end platforms. Okay. Finally, let's talk about optimizing. So these are the basics. They've been true for a while in Direct3D and other rendering APIs, but it's good to go over them. These are great ways to minimize bandwidth used. First, render opaque objects front to back with Z-buffering. If you can get a Z-reject, then you won't actually pay any cost for shading or loading textures. Make sure you do that. Second, as I mentioned before, alpha blending adds an I/O cost. It's going to cost you bandwidth, so make sure you only turn it on when you really need it. Third, large transparent areas, they aren't providing any visual impact. Don't render them. Make sure you use some geometry to trim large areas. So these are, pretty much oldies but goodies. Rendering techniques have been around for a while, but you really want to exploit them on these low bandwidth, power efficient platforms. Next, another old but good optimization. Direct3D has texture compression. The BC1, BC2, BC3 formats, those are available on pretty much every single machine. All Windows RT platforms, all Windows 8 platforms, you can always use them. They provide a huge bandwidth savings. They have a side benefit that your application will download faster. Pretty much if you have static content that compresses just fine, you really have to use these to fully exploit the platform. Something that's more of an old is new again. So Direct3D 8 and 9 had these 16-bit formats. They went away with D3D10. We've added them back for these low bandwidth platforms. These are useful on every feature level 9 machine, including all Windows RT tablets. They are optional on feature levels 10 through 11.1. New Windows 8 drivers support them, but if you happen to be running on a machine with older drivers, they won't be supported. So you have to deal with the optional behavior there. Your fallback is really you can use an 8-bit per channel format on those older drivers if you have to. Of course, you get half the memory bandwidth. If texture compression is causing artifacts that are unacceptable, this might be another alternative that will work really well. One important point to note is, unlike D3.9, these are texture formats only. They are not supported for rendering too. Okay. So I mentioned early on in the talk, the desktop is always composited now. What happened in Windows Vista, Windows 7, you run a full screen game, you get flickering, the UI changes, the transparency goes away. That's the desktop compositor turning off. We really didn't want that experience on Windows RT and Windows 8. We wanted the seamless experience, no flashes, apps just transition out. So what I'm talking about is, I can really flip in between these. No flickering. So in Windows Store, we removed full screen swap chains. Really, the only type of swap chain you can create is a core window swap chain with swap effect flip sequential. The reason for that is we wanted that seamless experience, but we didn't want to give up on the performance benefits of full screen mode. So the OS actually has the ability to automatically transition your window mode swap chain in and out of full screen and give you the optimal presentation behavior. There are a couple of key details to get correct in your application so the OS can take advantage of this performance optimization. One, the most important one and the easiest one to get wrong is you have to match the desktop resolution. I'm going to show you the code in a second how to do that. The catch is Windows Store apps are all device independent. You see device independent pixels mentioned. And you need to correctly convert from the DIPs, device independent pixels, to the actual pixel resolution of the buffers in the swap chain. There's an easy way to do that, though. Just create the swap chain with 0 width and height, and the OS will figure it out for you. You can then query the width and height off of those buffers. So I really, really recommend you do that. I'm going to show you the code in a second if you absolutely can't. The other thing you should know is when you create a sample D3D app in Visual Studio, the code for doing it correctly is there. Be careful how you change it. If you're off by 1 pixel, you'll see the performance decrease. And I'll show you what that performance decrease looks like in a second. Second detail to get right, the desktop is 32 bits per pixel, 4 bits per channel. You have to match the format right now to get the presentation benefits. Finally, the optimization is only while your app is the only thing on screen filling the screen. As other applications come on screen, the charms bar, you split screen it. We have to use the compositor for rendering all this on screen. So if you're doing performance profiling, make sure you maximize the screen and look to make sure you're entering this optimized mode. This is the code I mentioned in the sample. Basically, it's a conversion from the device-independent pixels. Then later on, you take the window width and height and pass them into the swap chain create. This is lifted straight from the basic D3D app that you can create inside Visual Studio. OK. So let me just start it again. Right now, this application is actually using optimized present. So what happened there in the transition, the desktop was being composited by the Windows compositor. As the application filled the screen and had the correct size buffer, it automatically transitioned, and the compositor stopped doing rendering work to get the content on screen. We can actually see that. Sorry, 1 second. In GPU view. And this is a great way to test if you have complicated window management code. Like say you have a UI, you want to show avatars or something, and you want to have like the ability to pick videos, and then eventually you go to a video playback mode. You want really efficient video playback in your application. And you're doing custom video playback. You can use GPU view to make sure that after all that UI management, when you finally get to the video, you actually have the performance benefits of this optimized full screen present. So first, this is what it looks like if you have optimized present. These vertical bars I turned on. It's the F8 key in GPU view. These represent the vertical blanks. This buffer right here, I can zoom in if it's hard to see. This buffer is coming from the application. This is actually the rendering of the cube in the background. You can see roughly the full screen performance benchmark that I showed earlier, same time. It's taking about 2.5 milliseconds for the frame. This looks nice and really clean. Let me go down and show the application. Down here, you can see the actual CPU thread on the application. The application's waking up, issuing a few D3D commands, and then it immediately gets the rendering up onto the CPU queue, which eventually makes its way up to the GPU hardware, executes there, and then gets content on screen. Nice, clean, easy to view. One thing I forgot to mention earlier, if you're learning GPU view, it's great to start with a simple app like this. The more complicated your app gets, you're going to have more buffers. There's going to be a lot of complexity going on in the UI. The simple app gives you a starting point to build up the knowledge on how to interpret these graphs really well. So this is what it looks like when you're getting the full screen optimized present path. There's just a single command buffer or a few command buffers. They're all coming from your application. Now here's what it looks like when there's just 1 pixel off. What I did is I modified the app. I subtracted 1 from the height, and we're out of the optimized path right now. This is, again, the application. It's running roughly, again, at the same time interval, depending on the clock of the GPU. And then here, we have the desktop compositor. It is also taking about the same amount of time. So composing the entire full screen swap chain, just 1 pixel off, takes about 1/8 of your frame time. As I mentioned before, you have a limited number of IOs per second. This is going to consume a couple of them. So it's really key if you want to maximize rendering quality of your app, get to 60 hertz, fast and fluid, make sure you stay in the optimized mode as much as possible. Okay. So that's optimized full screen present. Let's move on and talk about optimizations for tiled renderers. Everything up until this point has been general. It applies to immediate renderers and tiled renderers. Now this is about how to drive tiled renderers as efficiently as possible. There are 3 main areas to think about in terms of optimizing for tiled renderers. You're really helping the driver and the hardware manage that tile cache. So first of all, tiled renderers can only optimize within command buffers. As soon as you break a command buffer boundary, they have to write the cache out because some other application may then use the GPU. You only get cache efficiency while your application has time to use in the GPU. So minimize command buffer flushes. What causes a command buffer flush in D3D? 1, the flush API. That's what it's meant for. Presents, but you have to have that because there's no other way to get content on screen. Extraneous ones, really the ones you want to get rid of, those would be caused by things like calling map on a resource that's currently in use by the GPU. So let's say you have a scene, you filled in some content into a staging buffer, you upload it to the GPU. That upload is actually queued and doesn't happen until later in time when the GPU gets those hardware commands. If you immediately go and map that buffer right away afterwards, that means that the CPU has to wait for the GPU to consume those commands and execute them. You've caused a command buffer flush. We have to push those commands to the hardware and finish them before we can give you the buffer back. So really, you want to make sure you have enough resources to get a whole frame's worth of rendering in without having to map something a second time. The other solution, discard, no overwrite. What a discard is basically it's a hidden, queued reallocation of a surface. If you have a buffer, you map it discard. Under the scenes, the operating system will provide new pages to your application. The previous pages that are queued, going to the GPU in flight, those will progress through the rendering pipeline, go to kernel, be used by the graphics hardware, and the memory manager will automatically free them and recycle them for your application. Your second map will get a new fresh set of pages, won't stall, and you can fill them in at that time immediately without causing any stalls or flushes. No overwrite, same idea. It's basically a promise by you, the developer, that you aren't going to write over any areas that are currently in use by the rendering pipeline. You will get rendering artifacts if you happen to break that promise. Okay, so that's command buffer flushes. The second area is scene flushes. So this isn't quite as big a hit as generating a completely brand new command buffer, but you can actually cause a scene flush. A scene is, you've got a render target, you've started rendering to it with Direct3D, then at some point in time you decide, oh, well, I need another render target texture to go generate an environment, so you switch render targets. Tile-based GPUs have to complete the rendering on a per render target basis. Every time you switch, they've got to write the cache out, pull in caching for the new render target, render those, and then switch back. So really the way to think about this is, for each render target you have for a given frame, you really want to visit it once. So you do all your secondary resources first, then you go to your final swap chain buffer and you render that all at once. Second, this is actually probably one of the least well understood areas, but it's a really important one. If you are doing copy resource updates from CPU memory to GPU memory, if you update memory, it's not just about mapping them, but if you actually update memory in GPU memory that's currently in use by the graphics processor, it again requires executing all the rendering up to that point before the GPU can actually do the next update. And there's some hints we provide here. Use discard, use no overwrite on copy subresource region 1. It's the same semantics as map. Basically, it means that you want to discard the contents. There's no reason to keep them around. inside the tile-based driver, they'll actually allocate secondary pages and use those so the previous pages stay alive and it doesn't require a scene flush. No overwrite, again, you're promising as a developer that whatever you're copying from the CPU to the GPU isn't going to overwrite any data that's currently in use by the scene. Finally, the best type of tile cache optimization is telling the graphics driver that you aren't going to render to the tile at all. And this is just using the existing scissor rect functionality in Direct3D. Previous slide, this slide, it's all about discard. So we've also added 2 new APIs in Direct3D 11.1, discard view and discard resource. What this is about, when we talked about the tile cache, we read in from the tile cache memory, from main memory to the tile cache, render to it, then write out the results. That initial read is actually unnecessary if you're going to touch every single pixel in your rendering. Discard gives the hint to the driver that you're promising to overwrite every single pixel. The common way to use this, let's say you have a simple application, you just have a DirectX swap chain, you're going to render the entire screen, every single frame. There's no need to keep the contents alive and read them in for the next frame. So you present, first thing you do, you take the render target view for the back buffer, discard it. If you don't need it, don't keep it around, don't read it in. Okay, we're just going to sort of visually illustrate some of these optimizations. So first of all, discard. Let's say, every single pixel on this buffer is going to be written to. You call discard, that means that there's no longer each tile gets read in and then written out. There's just a clear that happens directly inside the tile cache, and then the tile gets written out. So instead of 2 full I/O operations over the bus, it's just going to be a write out at the end. That's how discard works. Okay. Next, scissor rect. Let's say that you're only going to render to this lower right-hand corner. What happens is when the GPU is iterating over the tiles to render, it's going to skip reading in and writing out all 3 of these, and it's only going to read in and write out that lower right-hand corner. Combine this with discard, where you can discard just a single region. You could actually set the scissor rect, discard this region. We'll do a clear on the tile cache and a write out just for that lower right-hand corner. And that's that. Okay. Finally, shader instruction throughput. I mentioned very early on, these new power-efficient GPU form factors have very limited shader instruction throughput. So they have another characteristic that we wanted to exploit in D3 11.1. They can increase their shader processing parallelism if you specify a precision level less than 32 bits per pixel. What we did is we added these new minimum precision hints to HLSL, where you can specify that the shader algorithm you're running actually requires less precision than a full 32-bit floating point number. The key here is these are hints and not data types. It isn't a guarantee that your shader is going to run at the lower precision level. So if you start to depend on behaviors or on the borders of, say, the difference between 16-bit and a full 32-bit float, you might see artifacts as your shader runs on a power-efficient GPU or it runs on a desktop GPU that's highly efficient at doing full 32-bit floating point. So, another detail, we use this a lot in the operating system. Direct2D effects, the image processing library I mentioned, it has some long shaders for doing really complicated blurs, things like that. We actually went and specified minimum precisions on the full shaders, and we get approximately a 20 to 25% improvement in throughput. We see the most gain from min16 float, which is good because that means don't spend a lot of time thinking about all these different precisions and how you can tune individual instructions. Just think, can min16 do all the shading algorithms I need? And specify that and try it out. In some corner cases, you might get additional shader parallelism out of min10 int, but the gains are only incremental over that 20 to 25%. So, start off simple and go from there. The last thing is, there actually is a cost to changing precision. I recommend just pick a precision level and do it for the whole shader. And again, in some corner cases, you might find benefits of switching. But some of these power-efficient GPU architectures, they generate instructions if you switch precision. So you may actually negate the whole benefit that you're trying to get to begin with. So here's an example. This is just a pretty common type of shader, pre-min precision hints. And this is what it looks like after hinting. Notice it's been consistently marked with min 16 float throughout the entire shader. And here's just an example of bad usage, where we've kept min 16 float to the top, marked the bottom as min 10 int. That div is only a single instruction. We're actually generating a second instruction to switch precision right there. Okay, those are all the optimization techniques. We've talked about, overview, what's new in Windows RT and Windows 8. What are the characteristics of the GPUs? We've talked about how to measure on the new platform. I showed you the tools that we've used internally that are available to you as well to optimize. Really the key here is optimize your application, get to 60 hertz, fast and fluid, and fully use DirectX 11.1 to create an awesome app experience. Thanks. So I'll take questions. I prefer to use the mics. Here are some resources that I mentioned in the talk.
Is there a way to detect if we're in a tiled renderer or not?
There is actually. So if you look in check feature support, there's a new type of feature we added in D3 11.1 where it actually tells you tiled render.
And all these features would be available if the GPU only supported like DirectX 9.1, I assume?
So we're talking about feature level 9.1.
Like we should still be able to detect tiled renderer and min 16 float and all that?
Absolutely.
Great.
Morning. I use GPU view, and sometimes there are two GPU queue, and only one is used. Why would it be? And in your sample, it was the same.
So there's some detail in terms of how GPU view visualizes the system. GPUs actually have multiple execution cores for executing GPU commands. It's a common mistake to think that all GPU queues are created equally. Usually there's only one 3D processing core, and the other ones are for specialized tasks. So you'll see one for video decode. You might see one for copying. So those only come alive when you actually use those specific API features. If you had a video playback app, you might see a queue for both 3D and you'd see a queue for video decode.
Actually, it was the case with me. It was video decode and rendering.
You may have been running software video.
No, we don't want that. But what I saw as well, that those queues, they will wait on each other. Let's say decoding, rendering will wait on decoding, and they'll block.
Yeah, so there are interdependencies between the two queues. You can actually visualize the synchronization primitives that go back and forth between the two. This is probably a much more complicated and advanced topic to talk about. I can follow up with you offline, actually, and we'll probably dive in deep there.
And second question, general. So what do you call power efficient GPUs? Is only that go to ARM architecture or on Intel as well?
These are both on ARM and x86.
So first question, when you performed all these experiments, did you have vsync on or off, and does it have any effect on how you would profile an application?
So that's good you asked. Key detail, you pretty much are forced at 60 hertz at all times in Windows Store applications. And that's why early on when I was talking about FPS measurement, you really don't want to call present because you'll be locked into 60 hertz. If you switch from present to flush, that makes your rendering independent of the update rate of the presentation stack.
Huh. Okay. And do you have, like online or somewhere, as a reference, good profiles of CPU to GPU, either context switches wise, or whether the workload is being balanced properly between GPU and CPU and stuff like that?
I don't know if we have example profiles, but in the resources section, I point to a really great GPU article, and it'll show you how to do a bunch of the analysis techniques that I just didn't have time to cover today.
Right.
And that you can get an idea from those analysis techniques of what to look for a good CPU-GPU interaction.
Okay. And can I use GPU view to find out the call stack?
Yes, you can. I don't know if I have the trace here. So for example, this is actually a stack walk event right here.
I don't know if you're connected.
Yeah. Sorry. So actually we have all these different stack walk events that are recorded throughout the sampling, and you can just see over time
Right.
where each core is.
And this wouldn't include my touch events. It would only include the app-dependent events.
So in terms of input processing, I don't know the ETW traces providers for those, but the input stack also has ETW tracing, and you can turn those on and watch input events happen on the same timeline.
Okay. Yeah, thanks.
I have a question has to do with the desktop duplication, the new set of API on Windows 8. My question is it available only on the desktop or available on both desktop and the Windows Store apps like ARM?
So desktop duplication is only available on desktop.
Thank you. The second question is, so which one saves the power more, like if I choose the feature level, the 9.1 or even higher, like 11? So if I go higher.
Generally, I wouldn't expect feature level to determine power. It's basically the same GPU. Really, it's about what type of rendering you do. So sometimes it's a misconception that using a lower feature level is more power efficient. We have some new features in 11 where if you're doing the same kind of rendering as you would have on 9.1, but you use some of the more advanced features, you might end up with lower power. It's really about what you do and not what level the GPU is.
Gotcha. Thank you.
Simple question. When you submit an application to the Windows Store, are there benchmark, or is there a baseline for GPU performance that must be met, or to provide the minimum requirements for fluid and?
I don't have the exact answer on all the different requirements. I think we can follow up afterwards. There are some requirements about how it looks.
Yeah, I think there are for touch as well. But,
yeah.
Okay, thank you.
Any more? I'll be up here after the talk and then afterwards in the networking area. So thanks again for coming. Hope it was useful, and have a good build.